We're asked to determine dz dt, or the derivative of z, with respect to t, given z equals x times e raised to the power of 2y, x equals t cubed, and y equals negative 3 plus 4t. So notice how z is a function of x and y, and then both x and y are functions of t. Before we determine dz dt, though, I'd like to take a look at this graphically to better understand what we're finding when we find dz dt, which should be a function of t. So here's the graph of our surface, and we have this purple point here which I'm going to animate from t equals 0 to t equals 1. Remember, both x and y are functions of t. So from t equals 0 to t equals 1, the point would take this path here. We're determining the instantaneous rate of change of z with respect to t, which we can think of as the change of height with respect to t. So when we find a value of dz dt using t values from 0 to 1, we'd be determining the instantaneous rate of change of the height along this path on the surface. Now going back to our work, again, because z is a function of x and y, and both x and y are functions of t, to find dz dt, we'll apply the chain rule given below, where dz dt is equal to the partial derivative of z with respect to x times dx dt plus the partial derivative of z with respect to y times dy dt. So we have dz dt is equal to, again, the partial derivative of z with respect to x. So we'll differentiate z with respect to x, treating y as a constant. And because the derivative of x with respect to x would be equal to 1, our partial derivative with respect to x would be 1 times e to the 2y, or just e to the 2y. And then we have times dx dt. The derivative of x with respect to t would just be 3t squared. And then we have plus the partial derivative of z with respect to y. So now we'll differentiate z again with respect to y, treating x as a constant. And because the derivative of e to the 2y with respect to y would be e to the 2y times 2, the partial derivative of z with respect to y would be x times e to the 2y times 2. And then we have times dy dt. The derivative of y with respect to t would just be positive 4. Let's go ahead and simplify. So here we'd have 3t squared e to the 2y plus, here we'd have 8x e to the 2y. Now we're not done here. Notice how dz dt should be a function of t, and right now we have dz dt in terms of t, x, and y. So now we need to substitute t cubed for x and negative 3 plus 4t for y. So we'd have 3t squared times e raised to the power of 2 times y is negative 3 plus 4t. And then we have plus 8x, and x is t cubed, times e raised to the power of 2y, which is again 2 times negative 3 plus 4t. For the last step, we'll go and distribute here and here. So we have dz dt is equal to 3t squared times e raised to the power, this would be negative 6 plus 8t, or 8t minus 6. Then we have plus 8t cubed times e raised to the power of, again, 8t minus 6. So again, if we were to evaluate dz dt, and let's say for any value of t between 0 and 1, it's going to give us the instantaneous rate of change of z with respect to t, or the change in height with respect to t. So going back to the graph one more time, again, just looking at the interval from t equals 0 to 1, the value of dz dt is going to give us the change in height at a given value of t from 0 to 1 along this path. And one more thing before we go, another way to find dz dt would be to write z as a function of t by substituting t cubed for x and negative 3 plus 4t for y. Notice how if we did that, it would give us z as a function of t, and then we could find dz dt without applying the chain rule. I hope you found this helpful.